Those also have a high nutrient load.
Yeah, we're getting a good slice of life here in terms of people interested in this.
All right, I'll go ahead and give my spiel. So good afternoon, everyone. My name is Sarah Grassi, and I am the Outreach Manager for COMIT. Thank you for joining us today. It's the first webinar for 2022. We had a good series in 2021, but took a solid break since then. And we will continue this webinar series over the coming months with a focus on a large range of topics related to our research goals, such as technological advances in seafloor mapping, which is what our speaker today will be talking about, and operational applications of hydrography, safe navigation, and beyond. I'm going to go ahead and link our website as well as our Twitter, the YouTube channel, which has all of our last year's recordings on it for the webinars, as well as if you want to sign up for our newsletter. I'm going to link those in the chat in just a second. Now I'm going to hand it over to COMIT's director, Dr. Steve Morowski, so he can introduce our distinguished speaker for today, Dr. Johnson Oguntuase. After the presentation, or Oguntuase, excuse me. After the presentation, you're welcome to participate in a brief discussion, so you can use the chat feature or raise your hand. You're welcome to leave your video on for the talk, so that we're not just seeing a bunch of, blank bubbles, but please keep yourself muted until the Q&A portion. So Steve, all you.
Thanks, Sarah, and I want to give a shout out to Sarah for creating what I think is going to be an excellent program during this year's seminar series for COMIT. A lot of new faces, a lot of interesting topics, and hopefully a lot of debate and making new contacts. So again, thank you very much, Sarah, for putting this seminar series together. And we'll have a few surprises as the year goes on. Really happy to introduce our guest speaker today, Dr. Johnson Oguntuase, from the University of Southern Mississippi. Dr. Oguntuase has a master's degree from the University of Nigeria in geoinformatics and surveying, and he has a PhD from the University of Southern Mississippi in hydrographic sciences. In particular, he's interested in low-cost global navigation satellite systems and inertial solutions for uncrewed surface vessels and other vessels. Today, his seminar is going to be on spatially advancing ocean mapping and ensuing technology. So, Dr. Oguntuase, the floor is yours.
Thank you, Dr. Steve. I'm happy to be with you today, and thank you for having me. And thanks to everybody for coming to join this webinar. So here we go. We will be talking about spatially advancing ocean mapping using emerging technologies. So like we all know, that recently, or maybe before I go deep into that, like you've heard about the introduction, this is my career path all the way from Nigeria, and now currently I work at the University of Southern Mississippi as assistant professor. We are located here at Stennis, as you can see right here. I'm pointing my laser pen at that picture that you're looking at there, here in Mississippi, at the Gulf of Mississippi. So we have a center called the Marine Science Research Center that was established a few years ago. I'm speaking to you right from this building, and we are also surrounded by folks at NAVO, NASA, Ocean Science Building, and Mississippi Enterprise for Technology. So we have a couple of other organizations that we are neighbors with here at the Stennis Space Center. And here is our oceanographic facility and some of the boats that we have here in the Division of Marine Science. So the Division of Marine Science do run an hydrographic science program. It's one of the oldest hydrographic science program in the United States. It was established far back as year 2000. And to date, it has graduated about 233 graduates from 34 countries, 17 MSc students currently, and about 4 PhD students current coordinator of that program is Mr. Batu, that some of you probably will know. I was with IHO some couple of years ago. So today's topic is about advancing ocean mapping using emerging technologies. Some of you are quite aware, or most of us are quite aware, that the autonomous driving cars or the autonomous industry is rapidly advancing, and the technology is relatively new. And because of that, there has been this surge in development or sensor development, various sensor integration happening to kind of achieve the whole goals and aims of the autonomous driving cars. And with all of that, that has also kind of created sensor availabilities, making them really affordable. Some of them LiDAR sensors, and also that snowballed into development of various platforms that we currently now have today, like the autonomous surface vehicle, underwater vehicles as well. And that also has led to the development of some sensors, especially the positioning and orientation sensors, that are now becoming more and more affordable, unlike what we used to have back in the days when they are quite a bit expensive. And then some of them, especially the GNSS sensors, you'll be talking about $10,000 or maybe $15,000 to acquire some of those. But now you do have sensors that are quite affordable and that we can integrate on various mapping platforms. Some of them, like the Wintra for drone mapping, sea surface vehicles, and all kinds of sensors that you probably can imagine are now cheaply available in the market. So to delve a little bit into the positioning component, because in ocean mapping, we are very, very critical about positioning accuracy, especially when we talk about mapping in the coastal waters, in the shallow waters, because of the under-key clearance that is very critical to navigation. Then positioning has to be very, very accurate, especially in the vertical component. And to achieve that, you will definitely need high accuracy positioning systems, and some of them GNSS. GNSS is the acronym for Global Navigation Satellite System, comprising the legacy system, which is the GPS, the Russian system, and now the newly emerging system, which is the Chinese Beidou and the European Galileo. Other regional systems too also exist, like the Indian system that is still regional, and the Japanese system as well. So, but both of them in the future will become global navigation system as according to their own goal. And by then we will be having more than 100 navigation satellites orbiting the Earth more than twice a day, for some of us who are probably familiar with that technology. But then there is this goal to map the ocean, and that was the GEPCO Seabed 2030 initiative, since the ocean occupies about 70% of the Earth's surface, and we have only mapped just about 20% of that to high resolution. And so the initiative is there to ensure that by 2030, we are able to map the entire ocean at a very high resolution, but that also is still very, very slow to achieve that. So it then requires that we employ force multipliers. Some of them are the autonomous surface vehicle and the AUVs and all of that. If you can integrate all of that, synchronize all of that, deploy all of that, and then work in synergy, we'll probably be able to achieve that goal. But then we'll see whether that goal is really achievable by year 2030. But so some of the motivation we have had here at the University of Southern Mississippi is to begin to see how we can evolve operational procedures that are really, really affordable if we really want to achieve that goal. You know, if we are investing like thousands of dollars in acquiring a platform and sensors, it's then become maybe a little bit more difficult to achieve some of those goals. And even for research purposes as well, if you can beat down some of the prices for platforms and sensors, and then we'll be able to do even more innovative research. So that's one of the motivation. And then a couple of years ago here in the University of Southern Mississippi, the team began to look at low-cost GNSS systems. Some of them are what you see here. This NetR9 is the geodetic grade, and our interest is to see whether in the vertical positioning they can actually meet some of the IHO requirement. So in the IHO requirement, you have different orders, and you have order 1A and B, you have order 2, you have the order 2 as well. But you even still have some other more stringent orders based on the most recent IHO S44 publication. But in this case, this graph you're looking at here is telling us what the expected error budget for GNSS positioning will be, and that's what you are looking at in the magenta here, which is about 15 cm. So the question is, if I use any of these low-cost GNSS receiver, what is going to be the performance? Can I achieve that 15 cm or certainty at 95% confidence level? So that's what you're about to see. So on the next slide, you're looking at the geodetic grade sensor. This is about $10,000, and then what you have at the top row is the receiver themselves. At the bottom row are the antennas, and then you can see the prices listed there. So then we begin to compare all of these systems in various positioning strategy to the performance of the geodetic grade system, and see if we can actually achieve that 15 cm or certainty I mentioned about. So to do that, we actually conducted like a series of experiments. I'm just listing a few of them here. So we had the receiver set up in what I call the zero baseline configuration. And sorry in case I'm using too much strategy, too much terminology. What that simply means is that all of the receivers are simply sharing one common antenna at the same time, and then looking at their solution comparatively. So I collected data in a minivan along this road at the Gulf of Mexico, and also collected some data on a boat all the way from the shore offshore, as you can see in these two diagrams that you're looking at. So the interesting thing that we noticed immediately was that the solutions are quite comparable to what you will likely be getting from a geodetic grade receiver. A first experiment that looked at the kinematic positioning of results from low-cost GNSS antenna at a static station is what you're looking at here. All the results I'm going to be presenting to you here and henceforth are going to be only the vertical component, nothing about the horizontal component, because that tolerance is easily achievable by almost any GNSS receiver. But then, achieving 15 cm is the big deal, especially 95% confidence level. And as you can see here, all the solutions are well within 15 cm, and the results are actually generated at 1 second's serial computation. So again, what you're looking at here is antenna to receiver pairings for each of these sensors that you're looking at. This column represents all the various pairings for each of those receivers and the geodetic grade antenna. So in other words, what you're looking at simply is telling us that, various antennas, we have various antenna qualities, we have impact on your positioning. So if you have an uncalibrated antenna, you do not expect that the solution is going to be as good as a calibrated GNSS antenna. But however, the solutions, you can also see what you're looking at in blue is actually the vertical component. And surprisingly, you will see that at least 2 of those low-cost GNSS antennas, GNSS receivers, compares very well with the geodetic grade antenna, receiver, which is the NetR9. And if you then look at the low-cost antenna here, this one that I'm talking about, you also see that the solution in the vertical component compares very, very well, with the geodetic grade receiver. So in other words, I'm telling you here that you can actually optimize low-cost receivers and then use them to achieve qualities that are similar to geodetic grade receiver. So I'm just going to skip over this slide because it's, we still have a lot to talk about today. And what you're looking at is still telling the same story, but using different positioning strategy. When the receiver is collecting data, in that van. And of course, also, you're looking at the statistical distribution here, and looking at the uncertainty for various antenna and various receiver and antenna pairings. But this particular plot that you're looking at in this column represents the lowest of the qualities of the receivers that you just saw in the previous slides. And of course, you can see why that the solution is drifting out of the tolerance with some bias over there. So skipping over that, on this slide, what you're looking at again are the solutions from another set of experiments that was conducted on a boat. Of course, again, you're looking at different positioning solutions and then the distributions of the histograms. So narrow histogram will indicate that you have a very good quality and performance, and your uncertainty are less biased than when you're looking at distributions that has histogram that has wide distributions. So let's click over this and look at the antenna phase center correction effect, especially for low-cost, some of the low-cost antenna. This is a very unorthodox kind of experiment that we conducted, but we have the aim to take this further and do actual calibration for some of the low-cost antennas that you just saw that has wider histogram distribution, and that way we can mitigate those uncertainties and then achieve better quality results even using low-cost antennas. So you might be asking yourself, why are we talking so much about the GNSS component? Because the GNSS component is very key if you're going to do positioning with GNSS and INS. You know that we usually combine both, in a navigation solution, and the GNSS will usually constrain the INS, especially when you are doing surface positioning, where the INS will usually drift very fast, especially when we talk. In a minute, we'll be talking about some of the different INS systems that we have in the market, and you see the more reason why the GNSS component is very critical. So this is still showing us some of the antenna phase center correction effects. In these plots, you're looking at solution from one single antenna. It's the same antenna, but we are applying different phase center corrections. And all the data collected on different days. The top row has the antenna oriented in the north direction, and the bottom row has the antenna rotated in the southern direction. Then you can see a kind of a mirror of the same distribution pattern you see in the horizontal component here. So if you flip the antenna from north direction to south direction, this is what you're going to get. So imagine that this antenna is actually roving and moving. Then it means that that's part of the reasons why you are seeing some of the low-cost GNSS antennas having wider histogram distribution, and of course creating some biases that we saw earlier. So this is one thing that is interesting to me, that I think if we can calibrate some of the low-cost GNSS antenna, will probably be able to get better results. And you might be wondering, why are they not calibrated? Well, you can imagine that you have in the market a low-cost GNSS antenna that you can buy, say, maybe for $300. The main purpose for manufacturing most of those GNSS antennas is not primarily for high accuracy positioning. It's mainly maybe for navigation, or maybe for in-car navigation and all of that. But then we are then leveraging, those available sensors because they are quite affordable, and then we want to see if we can actually use them for high accuracy positioning. That's why, those antennas most of the time are not calibrated. But the geodetic grade antennas, you will expect that those are calibrated, and it takes quite a number of quite a lot of efforts to achieve that. The technique for calibrating are not quite easily available. You probably may have to send them to some special centers to calibrate your GNSS antennas for you. So the INS component, so if you're not so familiar with what INS is, it's an inertial navigation system. It has IMU and it has a triad of sensors. If you're talking about the 9 degree of freedom, it will have magnetometer, accelerometer, gyroscope to measure your accelerations, rotations, and the earth magnetic field to be able to determine the heading. So you have it arranged like that, and then you have to implement the rotation matrix, you know, to be able to then output your solution with respect to the IMU sensor frame. So this is very important in our mapping, and of course we do have various categories of those INS systems, starting with the most expensive one, which is the navigation grade. Some of them we classify those as the mechanical INS system, the fiber optic gyro, the ring laser gyro, and some of those applications you will have to they have a specialty, you know, in meeting some demands in maybe space geodesy, or you have satellite launching to space that we need very high accuracy INS, or maybe you are deploying it on a vessel that has to go underwater, and underwater you don't have GNSS signals, because radio signals does not penetrate, electromagnetic wave does not penetrate that much into the ocean. In fact, almost zero penetration, except maybe you are very, very close to the surface of the ocean. You might be getting some very weak signal. So for those kind of application, then these navigation grade are very, very essential. And we do have some of them tactical grade, industrial grade, and automotive grade. And then you have this technology called the MEMS technology. And that's just evolved, you know, after the mechanical technology some years back. And then, but some of these are very, very cheap. Those are the kind you will have in your vehicle, your mobile phones, and all of that. But we do have the industrial grade. They are also affordable, but the tactical grade are not that affordable. They will range between, say, $5,000 to maybe about $25,000 or maybe $75,000. And then some of this navigation grade, you are talking about $100,000, maybe to $200,000 plus just for one unit. So you can imagine, if you want to do research and do all of that, investing about $200,000 or $100,000 on just one sensor, I don't think we'll be doing much of research. So that's one of the reasons if my attention is drawn to this segment of the IMU sensors, both the tactical grade, industrial grade, and see if we can actually use some of those, you know, for high accuracy positioning. So that leads me to the next segment of my discussion on low-cost GNSS buoy. You know, one of the motivation here is that we do have VDATUM, which is the Vertical Datum initiative by NOAA and US Geological Survey. I understand that some of those collaborations started back in Florida. Some of you probably might have some experience on that. And it was in a scenario or in a project where they had desired to provide seamless digital elevation model for Florida's Tampa Bay region. And then there was this problem then to synchronize all the various positioning datums. You'll be talking about ellipsoidal datum, tidal datum, and all kinds of datum that, you know, people usually reference their data set. But in navigation here in the United States, we will reference our navigation charts to mean low water datum, but then, you know, the shoreline will be referenced to another datum, and then the topography is referenced to mean sea level, and you then have various datum to deal with. So how do you synchronize, you know, all these various datums that will, you know, if you're not taking good care of that, using the geodesy knowledge, you'll be running into some risk of running aground ship, and that will cause litigation and all of that. So the NOAA initiative then gave birth to VDATUM, but then currently there are initiatives to improve on that, because it's been noted that uncertainty exists in the video room, maybe up to 20, 30 centimeters, and especially that most of the sensors that provide the models for the video room are all along the coast, our tide gauges and various sensors that we have along the coast. But then offshore, that becomes a problem, because you don't have, sensors deployed offshore to be able to do the accurate modeling as we would desire. So our interest, again, here at the University of Southern Mississippi, is to see if we can leverage some of these sensors that are coming from the automobile industry, and see what we can achieve with that. So some couple of months ago, we decided then to deploy a bottom package that is equipped with, CTD, conductivity, temperature, pressure sensors, and some other sensors. And of course, have this EcoBoat, this small boat that you're looking at right here, carry the GNSS sensors, low-cost GNSS sensors, as well as the geodetic grade GNSS sensors. First and foremost, the reason why we have both is to replicate the same experiment that we have done on land or close to the shore, and have that replicated offshore, and see what is offshore, or maybe in the car or in a static position, the dynamics of the antenna or the sensors, you can't compare that to when you are much further offshore. So that's what we are looking at here, and then we then want to see how much of certainty can we get, how closer is that low-cost GNSS is going to be to geodetic grade sensors that is going to cost us, say, about $70,000 or maybe $100,000. But then the results came out, these are initial results from that buoy experiment. What you're looking at the top is the time series solutions from GNSS observation epoch-wise, every 1 second are the result that you're looking at. The graph, the plot you're looking at here is the the EcoBoat drift, in the horizontal, if you're looking at it planimetrically. And these are the vertical solution for water level, reducing, the antenna position to the sea surface. And so what you're looking at in red is the average water level for a low-cost GNSS receiver. That sensor is just about maybe less than $1,000, and of course using PPP, which is the precise point positioning technique. That's another level of discussion which I would not want to go into right now. So, and then looking at that solution compared to an high-grade geodetic grade GNSS INS sensor, which is what you're looking at here in yellow, and then superimposing both solutions together, then you're looking at the difference between low-cost sensor, which is in red, and in green, the high-grade GNSS sensor. So it means that I think the variability you're looking at here, they are all less than about 5 centimeters. So that means that even a low-cost GNSS sensor deployed offshore can be of good value, in measuring water level offshore and providing even calibration for bottom package, to validate VDatum, and of course provide some measurements that, we constrain the VDatum model itself, and of course improve it. So this solution you're looking at the bottom package water level differences over time, using the pressure sensors that is on board, having removed the atmospheric pressure. And then you're looking at the blue line, which is the GNSS solution, and you see how both of them actually compare, and normally this is just about 3 centimeters. So that's an indication that we can take this further and then begin to predict our tide, even offshore, using a bottom package. If we can deploy array of bottom package, in the Gulf of Mexico, it then means that we can improve VDatum uncertainties, or maybe minimize the VDatum uncertainties, provide water level measurements, and then we begin to seamlessly kind of relate our our observations to mean low water in the case of navigation charts. So now this takes me now to another area of interest. This has become my fascination in recent time, especially that these are robots, and some of my generation likes to play a lot of games, although I don't play so much of it, but then I think this is a game for me. All right, so these are the this list of the team that has been involved in this project. This is an ERDC project. It's been on for like a year now, and our interest again is to collaboratively use these platforms to provide information that help improve ocean models. So like you are looking at here, you have 1V, you have IVA, you have C-Track, you know, all of these sensors, you know, being operated by various faculty members, and some of us are involved in using all of these three simultaneously. But then the major focus today will be looking at the collaborative measurement initiative between 1V and IVA, you know, to provide information for ocean modeling. So it's a kind of the idea is a kind of a backseat driver, even though some of us don't like the backseat driver because they just interrupt us. But sometimes the kind of information they provide might be very useful. So the algorithm that is happening here is that we have the vessel, which is the surface vessel. Each time IVA, which is the autonomous underwater vehicle, dives beneath the sea surface, it no longer have access to GNSS. It then has to rely on Doppler velocity log, you know, for its own positioning, orientation, and all of that. And once you command it, you know, with your mission plan, is expected to go to go along the planned route, you know, acquire data, water column data, you know, collecting data from various sensors, as you see in a moment. But then our idea is to provide additional information that is going to aid navigation. Say, for instance, we decide to change route, or we decide not to have a particular mission in mind, and we just want to explore the ocean. It then means that the surface vehicle can navigate at the surface, but how would the underwater vehicle know exactly where the surface vehicle is navigating? So we then have a radio integrated on top of the vessel that communicates with this IVA whenever it's at the surface, because it dives down and comes back up, then it can communicate. But once it's inside the water, we have an acoustic comms that is we have an acoustic comms, you know, that is installed on board the vessel that then pings the IVA, and then the IVA can obtain, you know, position locations from the surface vehicle, and then integrate that with its own current position, and then, you know, adjust its mission as necessary. So that is the idea, and we've been working on that. A team of scientists have been working on that a couple of months now. So these are the sensors that we have on IVA. We have on surface vehicle, which is the 1V, we have R2 Sonic 2020 installed. It's capable of bathymetry and multispectral water column. And the idea, like I mentioned earlier, you know, is to synergetic operation, mapping the water column, mapping, doing bathymetry, and everything that is possible, you know, in a synergetic mode. So this is kind of a replication of what I have mentioned earlier. You have the radio mast installed that high, but, you know, after a number of trials, we kind of found out that the antenna, the radio antenna we're actually using is a line of sight. You don't want to install it that high, otherwise it's flying above your signal, flies above your vessel, and you don't actually have good communication link between that. So we kind of change strategy from mapping it installing it at that high. The idea for installing it that high was that we wanted to have a control center on top of this roof, which is the MRC building that I showed you earlier, to have a team there, and then maybe have some cameras installed on top of the roof that can oversee, the coast as far as possible, and then monitor what is happening with our 1V with respect to collision avoidance. There is a camera on board the 1V itself that you can actually also use for that. But of course, as a backup, we want to have a backup camera monitoring system to be able to accurately monitor what is going on with 1V. One of the limitations currently with some of these autonomous surface vehicle and maybe most of the autonomous systems that we have currently in mapping, in the mapping industry, is that collision avoidance is still something that is a challenge that most people are still working on, as you may know. So this is a sample data coming from IVA, and temperature, density, salinity. Again, the idea is that once you have all this ocean variability, that we then don't need to sample water column frequently on our vessel. For those who are familiar with hydrographic survey operation, you do know that you want to always collect your sound speed velocity, because that is an integral part, in your multi-beam processing. Otherwise, your ray tracing will be very bad and your soundings are scattered all over. It doesn't make good sense. So I think this is interesting to me. We kind of accidentally stumbled on this. This was not something expected. You are looking at DM from a multi-beam survey that was conducted in the Gulf of Mexico across a channel. So this is the channel leading to the Gulfport, and across like this is shallow. It's just about 2 to 3 meters, and in the channel you have about 10 meters. So these are a set of lines. Both the line plan runs in the southwest northeast direction, and that's what you're looking at. For somebody who is not so familiar with multi-beam data set, you say, wow, this is a good picture. I like it. What a beautiful picture. But then, if you look at it critically, especially for those who are well experienced looking at multi-beam data, you see some kind of stripes running in there. You see some stripes. You say, this is a bad data. This doesn't look good. So what is happening? Well, we stumbled on this. This was not something planned, and it caught my attention, like I mentioned earlier. So you notice that for the southwest line, that's where you kind of have those, I will explain what that is in a moment, but you have those stripes. I just want to use a layman language now and just call it stripes. And then here, when you go in the northeast direction, which is about 50 degrees, you have kind of the stripes are not that evident. It looks like nothing is happening. Then the question is, what is happening here? So what is happening actually is that, maybe I should jump to the next slide, and I may come back here if necessary. So looking at this slide, you're looking at, this is the wind direction on the day this data was actually collected. The wind speed was 7 to 8 miles per hour, and we are actually surveying at 3 knots, right? So the wind direction is this way. And we all know the Ekman transport effect, that once the wind blows in a particular direction, you're going to generate a current that is about 45 degrees, from the direction of the wind. That's the surface current. And of course, because ocean has different density layers, you're going to experience the subsequent layers are also going to experience the same phenomenon. And of course, you have what we call the Ekman transport. So I call this the Ekman effect because if you look at this graph, you're looking at the direction of the wind, which is actually from south going to the north, and then create a surface current, and we are traveling directly opposite it. So that kind of created a rapid pitch effect, making the vessel to pitch so rapidly, much more than when we are actually traveling in the direction of the surface current. And that created the pitch effect that you are actually looking at here, which some of us will say that the pitch was not actually well compensated for, in this data set. And the magnitude of that pitch effect was actually about 20 degree, like you can see here, and the magnitude of the amplitude of the pitch is about 8 degrees here. So the higher the degree, the pitch angle, the less the multi-beam is actually compensating for that pitch effect. So that's what you're looking at here. And I think that is interesting to me. And I think maybe that may even generate maybe some future kind of research. Another interesting thing that you're looking at in multi-beam data set here, if you look carefully at this this screen, this is a remote monitoring of what is happening on 1V when we were actually collecting this data set. And we have the acoustic com, just like I mentioned earlier, in the collaboration effort between 1V and IVA. We have it installed here. This is not a good practice. We all know that mitigating sensors, noise in our acoustic in acoustic positioning, we know that there is always an interference. But the assumption is that if you have a frequency band, for 2 different sensors that are widely separated, in this case for the multi-beam sonar, it's between 170 to 470 kilohertz, and for the acoustic comms, it's between 22 and 27 kilohertz. You would think that there wouldn't be any interference, but if you watch carefully, you probably already seen some of those interference. And because we are pinging, the acoustic comp, pinging that to IVA, communicating with IVA at regular interval, you're looking at the effect here. That's the effect you see here as this noise, like that. And then I think that's also kind of interesting to us, telling us that, hey, we cannot put this guy here. Of course, we do know that, but our thought has been that, okay, they are widely separated. Maybe there wouldn't be so much effect like you just saw there. So I think from those previous slides, one of the take-home lesson, especially in the case where you face a wind, that is contrary to your direction of vessel, maybe a good idea then would be to plan your survey lines, to take advantage of the wind rather than traveling in the opposite direction, right? Because it might mess up your data big time, and it's resources lost, time lost. All right, some of the challenges that we are still facing that we're still hoping to conquer is that radio communication is still a challenge. You're probably expecting between 2 to 5 kilometers if you have some of the low-cost radio deployed on any of your surface vehicle. And there are other technology out there that we want to leverage, but we are still exploring those, and we see how far we can go with that. The main goal is to be able to operate those vehicles without supervision, without much supervision. Actually, right now, we can't say without supervision because we don't have obstacle avoidance. But what I tend to say actually is that we can remotely operate those without actually having a chase boat to follow after them in case there is something actually happens. So, and of course, power capacity is still a challenge. The vehicle I just showed you earlier, both of them are battery operated. You have to charge them and get them ready for emission. And maximum we've gotten out of some of them is about 10 hours, maybe to 12 hours, conservatively, so to say. So that's gradually bringing me to the end of this talk, and maybe I have run too fast that I wanted to give time for people to ask questions. Maybe I have rushed too much, but then I just want to present to you here, some of the work by some of our faculty members. This is Dr. Anand Hiroji. He's been working on mapping salinity and temperature distribution in the mouth of Mobile River, Alabama. USA using R2 Sonic 2020, and you can actually detect salinity using water column data set, and if they are well calibrated. So these are some of the research that we are engaged in, and we are still taking that further, developing even algorithms to be able to do in-house processing as well. And so these are some of his research interests and his teaching engagements. Also, Dr. Gero, who is also one of the faculty members here at the School of Ocean Science and Engineering, he's been developing a LiDAR, 360-degree LiDAR sensor, as you can see here, generating water point clouds for water column mapping and and all of that. So of course, it's been one of the teams as well. Dr. Hiroji, myself, and Dr. Gero have been working so much on some of the uncrewed vessels that I mentioned earlier. So I have the privilege talking to the director earlier, and we talked about collaboration. And I think the stronger the together, if we can collaborate, we'll be stronger together. And the earlier we begin to collaborate, the sooner we can achieve our goals for seabed 2030 and similar visions. And with that, I would like to thank you all for listening. And I apologize if I've run too fast and you can't maybe pick everything I've said, but this is now time to ask questions in case you have any. Thank you.
Well, thank you, Dr. Oguntuase. Yeah, very much appreciated. Excellent talk. Your whole focus on the practical aspects of surveying in nearshore areas is like music to our ears. People talk about surveying the deep oceans. Well, that's easy, and I think going through some of the practical limitations of the kit that we can generate, for doing nearshore. Which is a huge challenge because of beam spread issues, right?
Yes.
I think the kinds of things that you're talking about are really, really excellent. I see we have a number of questions. I guess I'll reserve my questions for the last part. So we'll start with Sarah. Do you have a question?
I think technically David was first. David, okay. You can go ahead.
David Nar.
Go ahead. That's fine, Sarah. Go ahead. I'll wait.
Okay. Thank you so much. The first thing that popped into my head when you were talking, particularly in the first part, about the low cost GPS antennas. So a project that is very, very much in its infancy, barely even started for us, is the crowdsourced bathymetry, and that's building off of the work that UNH has done in that space. Have you worked with them at all, or kind of the results of that?
Yes, I have. I presented, some of this work also at the Canadian Hydrographic Conference just at the beginning of COVID. Brian Carter presented something on crowdsourced bathymetry. Yes, I'm familiar with that. We had some chat on that as well, during that conference. That's doable. That's something that is doable, especially because of scarcity of data, and leveraging some of these low-cost sensors will be a good thing, going forward, with those kind of initiatives.
Yeah, absolutely. We're supposed to talk with them soon, and I feel like we should all kind of loop in together as we move forward with that project. So yeah, that was interesting. Thank you.
There's no sense inventing three wheels at the same time. David Nar.
Yes, very interesting presentation. Thank you. I was wondering about that 20-degree pitch artifact you were seeing on the survey you were just showing us.
Yes, sir.
It seems to me, well, first of all, that's a large amount of pitch, but I also used to think, though, that the POS-MV from Applinix, for example, could adjust and take care of that and make the corrections necessary. Or is this a result of the fact that you're trying to beamform up by 20 degrees and the beamforming can't adjust to that? I was just curious if you had any ideas of why that's such an artifact.
Okay, so to start with, the first thing is that the Applinix cannot compensate for that. The Applinix will only measure the vessel attitude. That's what it sees is what it measures, and it's measuring that accurately. And the problem is in the integration of the GNSS position with our acoustics returns. In the process of that's happening within the SONAR itself, in the SONAR acquisition software. And if it is not compensating for the pitch that is measuring, because the sensor is providing angular pitch measurement, and it is expected that the algorithm will be compensating for that in the beamforming, like you mentioned, and they'll stabilize, the pitch. right? So that nothing is swerving both back and forth. That's supposed to be stabilized, and then you will have good coverage at your seafloor. But that seems not to be happening in this case, in this experiment, especially when you see that, pitch, going up to about 20 degrees. It's kind of interesting to me too, because Dr. Anand Hiroji is one of our specialists here in bathymetry, like I showed you in that slide, and we got talking. It looks like it's an interesting talk for most of us, and we really want to explore that further. It's accidentally what we came across, because on a good day, we wouldn't have been surveying, in a wind that is about 7 nautical miles, but then accidentally stumbled on that, and of course it became an interesting study for us to look at as well.
Thank you.
Yeah. Matt Homar?
Yeah, I had a similar question to David. My first question was going to be which positioning system you had on the WAM-V when you were doing that survey. I guess it was the pause.
The ultrasonic is an integrated system, so you cannot even, bypass. You can bypass that.
Gotcha. Yeah, I had similar curiosity to David as to whether you might have been running into like a filtering frequency issue with the heave sensor, as well as a pitch issue if there was any crosstalk in there. And
exactly,
we could go way down the rabbit hole on this.
Exactly.
But yeah, no, it's an interesting problem, and I was wondering too about the effect that you described in combination with Anand's work that you were talking about. If it would be interesting to kind of blend those two and look at if you have, whether the salinity and temperature structure that he identified, is that pretty consistently stratified when you see that effect, or are you potentially, particularly when you are in the reverse direction of the current movement, are you getting any shear both at the sonar head as well as anything internal going on with that structure if you've got internal waves on the thermocline, technocline type behavior that are distorting your ray tracing?
Yeah, it's kind of interesting because, this is shallow water. We're looking at between 3 to just 10, and so all of those phenomena are kind of interesting that we intend to look at the data collected by the IVA, because it collected salinity, profiles that is run across, that particular survey area. Yeah, you're right.
Yeah, no, it was really interesting to see how much structure you're able to pick up with the R2, even in that very shallow water. It's surprising that it wasn't more well mixed.
And in fact, that data you just look at was collected at the beginning of March. That was March 1st. So we haven't even had time to digest the data.
Awesome. Well, look forward to seeing what you guys are able to do with it. That's really cool stuff.
All right, thanks.
Gotcha. Kat Dietrich, and then Young Gang.
Yeah, I think Young Gang was actually maybe before me.
Young Gang, you want to?
Yes, thanks for the interesting talk. My question is, did you use the wind data or any other physical oceanographic data to correct your bathymetry, those measurements? You mentioned the pitches and the different angles. You use the pitches to correction, or also use the wind? Okay,
so basically for acoustic ray tracing, what you will need is the sound velocity profile. So you get that from CTD, but that's typically what we do. We deploy our CTD, collect conductivity, temperature, pressure, and put that into your sound velocity empirical algorithm, and then you derive your sound velocity profile. So essentially what is needed for that ray tracing is sound velocity profile for and of course the surface velocity probe as well, you know, to kind of correct for all the ray tracing effect that goes into your multi-beam sonar processing. So to answer your question, we are not using wind in any form, but then we do see the effect of the wind generating current, you know, and that current, you know, creating the pitch stabilization that we talked about is actually, you know, pitching very faster than when we were actually traveling along with the wind. So that's what I saw in the data, you know, just about 2 days ago when I was trying to probe that. I saw that it's pitching much faster when you're traveling opposite the wind and pitch gradually when you're traveling in the direction of the wind. So that kind of created the effect that you saw.
Yeah, that's clarified my confusion. Thank you very much. In the meantime, I want to point out that you showed the wind-driven Ekman current, surface current, as 45 degrees to the wind direction.
That's on the surface.
Surface. That's for deep water only. For shallow water, like 10 meter isobars, the angle degree could be much smaller.
Smaller, yeah, you to be about 20 or less.
Yeah.
I do know that.
Okay.
Yeah.
Thank you.
Thanks, Young. Kat, Dietrich?
Yes, thank you. So I actually had similar questions, and based on your data and just looking at the inherent properties of the Ekman transport, it looks like the degree of impact was just obviously higher in the shallow areas, but were you seeing the same degree of, not error, but the impact of the 20 degrees, was that the same in the deeper part of the channel? I couldn't really see just based off of looking.
Okay, so this is still, maybe I should say that this is still our assumption. We cannot attach figure to exactly what we are seeing, but we do know that the currents created that effect that we're seeing, because you can actually see that in the motion data, right? So to answer some of those questions, then we need to get back into the oceanographic model and see actually how the current behave, you know, from in situ data themselves, you know, and see what is the angle of propagation for those surface current, whether it's actually 45 degree or less, or whatever that is. So, but at this moment, what we can actually see from that data is that there is a current that the wind is traveling in the south to north direction, and then that created what we would normally expect with Ekman transport. And in the Ekman transport, you can actually see that reflection in the pitch measurement. So that's what I can say for now. I will not be able to maybe provide, you know, facts and figures in addition to what we're discussing here.
Gotcha.
Thank you.
Nate?
Thank sorry. You, could I ask one follow-up question? Sorry. Okay. Related, I saw that you were a Category A certified, and I was just wondering how this helped you in your career and advancing through.
Well, you know, the Category A program kind of takes you through, you know, bathymetry class, acoustic class, oceanography class, and of course, because I went through the PhD program here, you know, went through the geology class as well, the chemistry class as well, the biology class as well. So kind of really diverse background. And then you then major in hydrography, which is positioning and oceanography. And of course, physical oceanography as well.
Awesome, thank you.
Yeah, we're dealing with all this right now, and Dave Nar can attest in terms of getting our hydrography program up and running. We have a guest from Navico, Ryan Sullivan. Would you like to ask your question? Hello, Ryan.
Ryan, it says you're unmuted, but we can't. Yeah, we can't hear you. It might be a setting with Teams.
Yeah, you want to just.
If you want to try the chat.
Yeah, put your question in the chat, Ryan. What is the minimum depth at which you can get accurate data? That's an
a big
open-ended question, isn't it?
Yeah. There's, mainly the challenge in shallow water is your footprint, and being able to also stabilize your beams for your multi-beam data. That's why the director was mentioning earlier that it's a lot easier to survey in the in deep waters, because most of these challenges then disappears into the uncertainty, right? But then in shallow water, the uncertainty that is expected is very, very small and quite challenging to achieve. And that's why we are facing all of these challenges. Perhaps if we were surveying in a water that is about 100 meters deep, we wouldn't even be seeing this artifact that we are talking about. But because we are in shallow water, the resolution is very high. And then all these challenges crop up. So achieving accuracy is really the big challenge, in shallow water. And I don't think you are able to actually put a number in terms of accuracy, though maybe in shallow water for some projects using this GNSS INS technique, maybe you are able to achieve, if you really work hard, maybe you're able to get it down to maybe like 10 cm, maybe if you really work hard, maybe 10 cm. So 95% confidence level.
I know we need to get have you leave it right at 1 o'clock, which it is right now. I would like to ask you one quick question, if that's okay. Okay. It seemed like we're getting our surface vehicles smaller and smaller and lighter. And I wonder if this is resulting in this consequence of high pitch levels, right? That if you had a heavier vehicle, it wouldn't pitch so much, right? So, yes. We have two, trends that are going in opposite directions here, right? Exactly.
That's true. You are accurate. You are accurate about that. Maybe if it has been maybe one of our traditional vessel that we had deployed, maybe we wouldn't have seen this. This is not something that we see every day, but then we ran into it because we are using a lighter vehicle. You can actually use a single hand and pull that vehicle when it's sitting on its trailer. Just a single person can move that, and you can try that with some of the surface vehicles. With some of the traditional vessels that we use for mapping, and it wouldn't be pitching that much. And if you also look at that vessel, it has something kind of a spring. Maybe if I can show it on my slide. I don't know if that is up now. Yeah, I think it is. Okay. Anyway, it seems I lost my slide. Anyway, so what I'm trying to say is that it has that spring, and more so like what Matthew was talking about. There's a lot of drag around the multi-beam itself as well, because we don't have a fairing installed, and that's one of the things that we have considered, that maybe if we have a fairing, it kind of pushes the interference of water currents at the surface, minimize some of those effects. Maybe that would be one of the ways to take care of that problem. And maybe there is a way to develop an algorithm, in collaboration with some mathematicians, and then come up with a solution. If we can decouple the effect of the wind somehow, only God knows, maybe that is possible or not. Maybe it might be an interesting topic for some of us to look at. So you're right, yes. The lighter the vessel, the more it will pitch, and some of the challenges will occur.
Gotcha. We just had a note in the chat from Dennis Haynes at H2I in Canada that Cat A training is an asset, and hydrographic surveying certification of individuals is also an important asset in the community. So good point to make, and we should all get certified.
Yeah, and I think I should have been mentioning that as well. I was trying to rush over this, not to waste time. That is called hydrospatial. Mr. Dennis has been the pioneer of that, and I think we should also be collaborating in that in that respect with him and what they're doing up there also in Canada. It's one small community, and the more we collaborate, the faster we get to our goals.
Yep. Excellent. And, I think if we can share courses, for example, online courses, that we don't necessarily all have to have the entire suite of courses in order to, make these programs work. So, we might think about collaborating on those lines as well.
Yeah.
Well, thank you so much for the seminar. You can see by the number of questions, a lot of interest in what you're doing, and it's really timely that we have this level. So I want to thank you again. So please either clap in acoustics or other ways. And thanks again, and very much appreciated.
And thanks so much, Sarah, for inviting me. It's been a pleasure working with you.
Absolutely.
Thank
Thank
you
you so much. I'm sure we'll be in contact.
Sarah,
Thanks,
right.
everyone.
will you remind us our next seminar speaker and when it's going to occur?
Oh, put me on the spot.
Oops, sorry
Hold
about
on.
that.
I should know that. No, it is going to be next month, and I put it in the chat. I believe it's from College of Charleston, one of their professors there, Leslie.
Sauter.
Of course, here. Yeah.
Leslie Sauter, yeah.
Leslie Sauter, yep. And I don't have her abstract yet, but that'll be actually not next month, May 25th. Instead, we're skipping April. So yeah, Dr. Leslie Sauter from College of Charleston.
Thank you. Sorry to put you on the spot there.
No, that's okay.
We'll certainly send out the notification. Thank you all again for attending, and have a great rest of your day.
Thank you, and thanks for having me.
Bye, everyone.
Thank you,
Thank
Johnson.
you.